Okay, so hopefully you had a good holiday weekend. Remember, we have class again tomorrow. Um, and then exam two is going to start on Friday through Monday. And please remember that Saturday the testing center hours are a little shorter, and on Monday they close 2 hours earlier than usual. So just remember those things. Um, Today we're going to continue our discussion from chapter 22 on carboxylic acid derivatives. We'll talk a little bit about their spectroscopic properties, interesting esters and amides, and then we'll discuss the reaction they undergo, the nucleophilic acyl substitution reaction, which we've already learned back in chapter 20, so we already know the mechanism. But we're going to be using different types of nucleophiles than what we used in chapter 20. Before we do those things, one other announcement. There is, on Thursday, we're going to have our Zoom online exam review, the question and answer session. We're going to be filming the review, the review of the topics and the outline tomorrow. So by tomorrow evening, that's going to be online. So you should take a look at that and then come with questions Thursday at 7. I'll send out that Zoom link sometime tomorrow. So, and one last item on nomenclature. Nomenclature of nitriles is very simple. If it is a straight chain nitrile, you just tack the word nitrile onto the end of the number of carbons in the chain. And then the carbon in the nitrile is going to be carbon number 1. The nitrile of benzene has its own common name that is acceptable in IUPAC nomenclature. It is referred to as benzonitrile. And then sometimes the nitrile functional group is a substituent. If it's coming off as a branch, as a substituent off of a larger chain, if it's not at either end of the chain, then it can be referred to as a cyano group. And that also works when you have a nitrile coming off of a ring. It would be a cyano substituent off of a ring. Okay? So we have a table here from the book that nicely summarizes the nomenclature of our carboxylic acid derivatives. On Friday, we skipped over the thioester. It's very, very similar to the ester, just with two differences. You have the phrase thio in front of the 8. Thio refers to sulfur. And then you have to put an S in front of the alkyl group to indicate that it's attached to a sulfur. Okay? Are there any questions about the nomenclature of our carboxylic acid derivatives? Good. Let's briefly summarize their physical properties. This table does that. And this is not carboxylic acids because we covered those in chapter 19. This is only the derivatives. And what we find is that amides are going to behave differently from all the rest. So all of our carboxylic acid derivatives, except amides, have very similar boiling points because they have dipole-dipole interactions with each other, but they are unable to hydrogen bond. So there are some differences in boiling points, as you see here from this figure, but they're slight enough, and also they're not really predictable in terms of saying that esters would always be higher than acid chlorides, for example. So we're just going to lump these compounds all together and say that with the exception of the amide, our carboxylic acid derivatives of similar shape and size will have similar boiling points. But the amides are going to have much higher boiling points than our other carboxylic acid derivatives because of the ability to hydrogen bond. However, that applies, as it notes here in the figure, only to primary and secondary amides. Why not tertiary amides? What are tertiary amides missing? The hydrogen. There's no NH. So the tertiary amides are going to be in this category with the rest of these carboxylic acid derivatives. It's only the primary and secondary amides that will have higher boiling points because of their abilities to hydrogen bond to each other. And then we have the solubility properties. They will be comparable because all of our carboxylic acid derivatives are capable of hydrogen bonding to water molecules. So the standard rule we've learned of five carbons or less for each group capable of hydrogen bonding to water, dictating the water solubility. Any questions about the physical properties? Okay, let's look at the spectroscopic properties of our carboxylic acid derivatives, and we'll start with IR spectroscopy, where the key peak in the IR spectrum is going to be that carbonyl stretch, that carbon-oxygen double bond stretch. Very, very prominent. Shows up between about 1650 and 1800. Here we have a table showing the CO stretching frequency of the different carboxylic acid derivatives. And we see something interesting. We see that as we go down the table here, the Z group is getting more basic. And as it gets more basic, you see that the absorption frequency is decreasing. Okay? So there's no need to memorize these numbers here. That would be an absolute waste of your time. But what is important to note is this trend, the trend that as the basicity of Z increases, the value for that CO stretching frequency decreases. So we should be able to explain why that is the case. And to do so, we have to go back to the law that governs the position of our stretching frequencies in the IR spectrum. Whose law governs that? That was one of the last things we did in person before Thanksgiving. Hopefully you can remember that far back. And it is actually something that's usually treated in a physics class. So maybe that gives you... Hooke's law, yes. Hooke's law is the law that governs the motion of weights on the end of a spring. And so our stretching bonds, we pretend that they are the atoms are the weights and the bonds are the spring. Okay. So based on Hooke's law, would a stronger bond require higher frequency or lower frequency radiation to stretch? Higher, exactly. So in the Hooke's law equation, the term that's related to bond strength is in the numerator. Okay, so the stronger the bond, the higher the stretching frequency. Okay, so what this is telling us is that that carbon-oxygen bond is the strongest for the acid chloride and is the weakest for the amide. Why is that? Yes, Sydney. Yes, exactly. Okay. Do you want to elaborate on that just a little bit, or? Okay. Okay, so we have our, very good explanation, we have our minor contributor in each case where the Z group is donating its lone pair to the carbonyl, and we have a carbon Z double bond and a carbon-oxygen single bond. The more basic Z is, the more prominent that minor contributor becomes. Okay, so with nitrogen being the most basic of these atoms, that minor contributor contributes the most for the amide, which means that as your carbon-nitrogen bond order is increasing in the hybrid structure, your carbon-oxygen bond order is correspondingly decreasing. And that's reflected in the lower value for that absorption frequency. Then here with the acid chloride, you have only a very small amount of donation because chlorine is electronegative. It's holding on to its electrons. Plus, it's a third row element, so that bond is longer. Those electrons are further away from the carbonyl carbon. So you have a very, very small contribution from the minor contributor here, meaning you have a high carbon-oxygen bond order. Down here, we have a lower carbon-oxygen bond order. because we have some partial double bond character between the carbon and the nitrogen. Okay? So you shouldn't memorize these numbers, but you should be able to explain why the CO stretching frequency of the acid chloride is the highest of these compounds and that of the amide is the lowest. Any questions? Okay, so our nitrile does not appear in the table, but it's in this chapter. The nitrile has a carbon-nitrogen triple bond, and since triple bonds are stronger than double bonds, as you would expect, the stretching frequency is higher than it is for the carbonyls. And this is the value right here, about 2250 wave numbers or inverse centimeters, which is very comparable to that of the alkyne. Okay. Let's talk briefly about NMR spectra, some key chemical shifts in the NMR, both the proton and the C13 NMR of our carboxylic acid derivatives. So the alpha hydrogens, those are the hydrogens that are adjacent to the carbonyl on the carbon, hydrogens that are on the alpha carbon. Those are slightly de-shielded inductively by that carbonyl group, that partial positive charge on the carbonyl carbon. So those are going to show up between about 2 to 2.5 ppm. If there was no de-shielding, alkyl hydrogens usually show up between 0.9 and about 1.5. So this is de-shielded by roughly 1 ppm relative to a typical alkyl group. Another type of hydrogen that we see, the NH of an amide. Okay, so an amide NH is going to be between 7.5 and 8.5 ppm. So this hydrogen is also de-shielded by the carbonyl group, but because it is attached to an electronegative heteroatom as opposed to a carbon, it is de-shielded significantly more than those alpha hydrogens. So it has two features that cause it to be de-shielded and to appear downfield. Okay. Now in the C13 spectrum, the key chemical shift is that of the carbonyl group, and our carboxylic acid derivatives in general are in the 160 to 180 ppm range. Okay. If we were to compare the carbonyl groups of carboxylic acid derivatives to those of aldehydes or ketones, would these appear upfield or downfield of aldehydes and ketones? Upfield or downfield? And I'll give you a hint. If you're trying to remember what upfield and downfield are, the physicists messed up the definitions for us, and downfield is a higher number. Okay? So downfield would be higher number, upfield would be lower number. Yes? They appear upfield at a lower number, and why is that? So the aldehydes and ketones are usually 180 to 200. And why is that? With, what was that again? Basicity, yes. So it's the same explanation we have here, where the basic Z group is donating electrons to the carbonyl, which is causing shielding, and that shielding moves the chemical shift upfield compared to aldehydes or ketones. Okay? So again, not necessary to memorize the numbers, but to understand that our carboxylic acid derivatives will show up at a lower chemical shift value than our aldehydes or ketones. And then the nitrile, the carbon of a nitrile, that's going to be at about 115 to 120. And is the carbon of a nitrile going to be upfield or downfield from the carbon of an alkyne? Higher number or lower number than the carbon of an alkyne? Okay, downfield at a higher number. Why? Exactly. So you have not only the effect of the circulating pi electrons of the alkyne, which we covered in chapter 14, but you also have the electronegative nitrogen deshielding or withdrawing electrons. So most alkynes show up at around 80 ppm. Again, not necessary to memorize those numbers, but it's more important to be able to explain why a nitrile carbon is going to be downfield at a higher chemical shift value than an alkyne carbon. All right, any questions on spectroscopy of carboxylic acid derivatives? Okay, let's talk about interesting carboxylic acid derivatives in nature and medicine. And that's mostly going to be esters and amides, because our other derivatives are usually used as reactive intermediates to synthesize esters and amides. Esters and amides are the ones that typically are stable enough to be present in nature. One common feature of esters is that they smell good. Those of you who are taking the 354 lab, have you synthesized an ester yet? I see nodding heads. What did it smell like? It smelled like bananas. I think you made isoamyl acetate or something similar to that. It smells like bananas. Other esters smell like pineapple. There's one that smells like wintergreen. So esters have a good smell. And the ones that exist in nature are like that. They provide the fruity odor. Despite the fact that esters smell good, they make terrible perfumes, and we'll explain why later on in the chapter. Okay. So cyclic esters are lactones, and there are many different lactones that exist in nature. Vitamin C is one of the more famous ones. Ginkgolide B is part of ginkgo biloba extract. This is something you can buy at a health food store. It's used in Chinese medicine for a variety of purposes. Some believe that it enhances your memory. Whether that's true or not, I'm not sure, but it is a popular substance, and ginkgolide B is one of the main constituents of ginkgo biloba extract. And you see it has 3 lactones. So the lactones in ginkgolide B and vitamin C are 5-membered rings, so 5- and 6-membered lactones are very common in nature. But there are also a fair number of macrolides or macrocyclic lactones that have much larger rings. FK506 has a 21-membered ring. You see right here, there's the ester, and here's the 21-membered ring. FK506 is a naturally occurring compound that is an immunosuppressant. So you might wonder, why would you want to take something to suppress your immune system? It tells you right here, if you've had an organ transplant, you need to suppress your immune system to prevent it from rejecting that foreign organ. So you would take FK506 or something related if you had an organ transplant. Okay? So that's just scratching the surface of interesting esters and important esters. As far as amides go, proteins are going to be our most important amides. Proteins are polyamides, usually 100 or more amino acids linked together by amides. And we'll have much more to say about proteins later on in the semester, as well as their shorter cousins, peptides. They get their own chapter. There are other amides that are common both in nature and in medicine. And the one we'll show you today is Gleevec, an anti-cancer compound, also known as imatinib. Here is the amide of Gleevec. And Gleevec is one of the most important anti-cancer agents. It was introduced about 25 years ago, and it marked a real shift in the treatment of cancer. Because classical anti-cancer compounds, such as the ones based on mustard gas that we talked about last semester, typically work by interfering with the cell cycle, preventing cells from dividing. And so they indiscriminately kill all cells, but they kill more rapidly dividing cells the fastest. Of course, your hair cells divide rapidly, so that's why people's hair falls out when they're undergoing chemotherapy. And so it's difficult for doctors to give patients the exact right dose of a classical anti-cancer drug to only kill the tumor and not to kill the patient. That's why chemotherapy is such a grueling process. But as we learned more about molecular biology and biochemistry, we learned about mutated proteins in cancer cells, in tumor tissues that are not present in normal cells. And so if we could design molecules that would selectively inhibit these proteins that only exist in cancer cells, then we could much more selectively kill cancer cells without killing normal cells. And so Gleevec was one of the first, if not the first, of these more modern and selective anti-cancer agents to be developed. So it is a kinase inhibitor. Kinases are enzymes that are part of cell signaling pathways, including the pathways that signal cells to divide. Most cancer cells have mutated kinases that signal the cells to divide out of control. And so once we identified these mutated kinases and learned about their structures, we could design molecules that selectively inhibit the mutated kinases, but not the normal kinases. And that's what Gleevec does. It selectively inhibits a kinase that is present in a certain form of leukemia cells and also in a certain type of stomach cancer. So if you have those two types of cancers, Gleevec is the drug you would take, and it's incredibly effective. And since that time, there have been many, many more of these selective anti-cancer drugs for very specific types of cancers. Okay? And the key part in this chapter we're looking at is the amide. All right. So let's talk about the reaction that our carboxylic acid derivatives undergo, and that is the nucleophilic acyl substitution. This is a reaction we've already learned back in chapter 20. We learned this reaction, and we learned it with two types of nucleophiles. We learned it with metal hydride nucleophiles for reductions, and we learned it with organometallic reagents such as Grignards and organolithiums, our nucleophilic addition reactions. Okay, so we can have a nucleophile negatively charged, or at least a strong partial negative charge for the nucleophiles from chapter 20. From this chapter, we're going to have some neutral nucleophiles. We're going to have alcohols. We're going to have amines. And so the product is going to be a new carboxylic acid derivative. The byproduct, if we have a neutral nucleophile, or if we have an anionic nucleophile, the byproduct would be the leaving group as an anion. If we have a neutral nucleophile, it's going to be the conjugate acid of that species. And if this is a strong acid, then we're typically going to have a base to neutralize that, because usually we're not trying to produce strong acid in these reactions. So we have here the general mechanism. We've gone over this mechanism before. So we have attack of our nucleophile generating our tetrahedral intermediate, followed by elimination of our leaving group, giving our desired product, and then displacing Z. So the relative reactivity of our carboxylic acid derivatives is going to depend on, well, the nature of our Z. Okay, so we look here at this table. We have increasing leaving group ability, and we have that correlating with increasing reactivity of these carboxylic acid derivatives. Okay, so why are these properties correlating? Which of the two steps in that mechanism for nucleophilic acyl substitution is going to be accelerated if we have a better leaving group attached to our carbonyl carbon? Which of those steps would be accelerated? First step. Why? Okay, so if you have a better leaving group, it's less basic. It's not donating electrons as strongly to the carbonyl carbon. So you're going to have a higher partial positive charge. That's exactly right. So the first step will be accelerated if you have a better leaving group, a less basic group attached to the carbonyl carbon. What about step 2? Is that going to be faster as well? What's happening in step 2? Let's go back. The leaving group is leaving. Okay. The better leaving group will depart faster. So both steps of the reaction are impacted by the nature of the leaving group. Okay. So both step 1 and step 2 will be faster if you have a better leaving group. Now, let's say that your nucleophile is a better leaving group than Z is. What's going to happen to your tetrahedral intermediate if the nucleophile is a better leaving group than Z? Sydney? Yes, you'll just revert back to the starting material. Your nucleophile will depart as opposed to Z, right? Your better leaving group is the one that's going to leave faster from that tetrahedral intermediate. So what that means is that we can only convert more reactive carboxylic acid derivatives into less reactive carboxylic acid derivatives. Okay? So if we go back to this chart here, if we have an acid chloride, we already have the best leaving group of all these options on the carbonyl carbon. So we could add any of these other species as nucleophiles and obtain any of the other types of carboxylic acid derivatives. Conversely, if we have an amide, we've got our worst leaving group, and we're not going to be able to convert the amide into these more reactive carboxylic acid derivatives because the nucleophile would just depart from that tetrahedral intermediate. Okay? So with that knowledge, we should be able to look at individual reactions and decide whether or not they will proceed. So please get your eye clickers out. Go ahead and talk to your neighbors and decide which of the 3 reactions shown there will readily occur. And don't everybody talk at once. This group is always quieter than the 10 o'clock group. All right, let's try to get our final answers in the next few seconds. Okay, good. A few more coming in. Any more? Going once. Going twice. All right, that looks like all of our answers for today. Number 1, reacting an amide with an alcohol to get an ester. Will that work? No, that won't work. The nitrogen, this is a better leaving group than that. Number 2, acid chloride and alcohol to get an ester. Will that work? Yes, right? We can convert an acid chloride into anything else. Anhydride plus alcohol to give ester. Will that work? Yes, the carboxylate is a better leaving group than the alkoxide. Very good. So we can predict the reactions that will occur. So here we have a figure showing us generally the types of reactions we'll see in this chapter. We would use carboxylates as our nucleophile to generate anhydrides. And we could do that from anything more reactive than an anhydride, so that would only work with an acid chloride. Conversely, we could use amines to react with any of our carboxylic acid derivatives, and we would generate amides. So you might wonder, if an acid chloride is our most reactive species, how do we make it? The answer is that the carboxylic acid itself has unique reactivity that is inherent in the acidity of that functional group. And so we actually have special reactions that we'll learn tomorrow that allow us to convert carboxylic acids to all of our carboxylic acid derivatives. Okay? And then you might wonder, what about amides? Do they react at all? They're the most stable. Well, the flip side of what I just told you is that all of our carboxylic acid derivatives can be converted into carboxylic acids themselves. So we will learn ways of making carboxylic acids from amides. Okay? But we're going to start out by looking at the reactions of acid chlorides. So I've written it generally here on the board. We're going to react an acid chloride with a nucleophile. We're going to displace the chloride because the chloride is going to be a better leaving group than any of the nucleophiles we're using. We're going to form HCl as a byproduct. Usually we don't want HCl, so we're going to have pyridine as a weak base to neutralize that HCl. I've written it kind of separately here at the end just to emphasize its role, but usually we're going to add it simultaneous to adding our nucleophile, and we'll see where that comes into play in the mechanism. So the acid chlorides are our most reactive carboxylic acid derivatives, and that's evidenced by what we see here on the screen. This is a bottle of acetyl chloride, the acid chloride derived from acetic acid, and if you look closely, you see some vapor coming out the top of that bottle. You wouldn't want to sniff it, you wouldn't want to stick your nose in there, because that vapor is the HCl that's being given off. And what's happening? Well, there's water in the air. All air has water present. So if you expose an acid chloride to the air, it's going to start reacting with the water in the air to produce the carboxylic acid and the HCl. Right? You don't just put pyridine in the bottle, so you're just giving off that HCl. And there it is right there. Okay? So I don't know, the author of our textbook is based at the University of Hawaii. I don't know if she took this picture from her lab or not, but of course the air in Hawaii is very humid, is loaded with water, and so this reaction would happen much faster in Hawaii than it would here in Utah in a drier climate. So usually we don't want that to happen. We don't want our acid chlorides reacting with water because it takes effort to make acid chlorides from carboxylic acid. So you're not just going to expose it to water and get back what you started with, okay? But what you do typically want to react acid chlorides with are alcohols, because then you can convert the acid chloride into an ester. So let's draw the mechanism of that reaction. Here's our acid chloride. Here's our alcohol. Step 1, our alcohol is going to attack the carbonyl carbon of our acid chloride. But since we used a neutral nucleophile, a weak nucleophile, we have a positive charge on that oxygen. So here's where we're going to do our proton transfer. our pyridine is going to function as a weak base and deprotonate. So here we're generating the pyridinium ion. Okay, looking like this. So now we've made it to our tetrahedral intermediate. We see that chloride is a better leaving group than our alkoxide. And so when we reform the carbonyl, it is the chloride that departs, and that generates our ester. We also form chloride, and that chloride just forms a salt with the pyridine. Okay? So we have our nucleophilic attack. We have deprotonation, that proton transfer, and then we have elimination of the chloride. Any questions? Yes? Yep. So this lone pair taking that. So the problem you'd face there is it would be a 1, 2, 3, 4-membered cyclic transition state. And so there would be some strain in that transition state, and that would cause that intramolecular proton transfer to be slower than the intermolecular proton transfer. Okay? And that's good because we want the negative charge here to reform that carbonyl and eliminate out the chloride. Okay? Good question. Any others? So if we react an acid chloride with a carboxylate, the conjugate base of a carboxylic acid, now we have a negatively charged nucleophile. And so here we don't need the pyridine because we're not producing acid. So our carboxylate attacks. Here's the tetrahedral intermediate that is generated. The chloride is a better leaving group than the carboxylate. So when this collapses to reform the carbonyl, we're going to displace the chloride, and our product is going to be an anhydride. So when we're making anhydrides from acid chlorides, we don't need the pyridine because we're not forming acid. Now the chloride is going to form a salt with the cation. We didn't draw the spectator cation, but this carboxylate probably has either a sodium cation or a potassium cation or something of that nature that came with it that just forms a salt with the chloride. So pyridine would be used with alcohol nucleophiles. It would not be used with the carboxylate nucleophiles. Any questions? So our other type of nucleophile that we would have is an amine. And when we use an amine in reactions with acid chlorides, we use two equivalents of the amine. Okay? So I'll draw that for you. So here's a aromatic acid chloride. We're going to be using diethylamine in this case. We're going to be using two equivalents. And we're going to be generating an amide. This is one that most of you have heard of. Most of you have probably used this one before. This amide is referred to as DEET. What is DEET used for? Yeah, it's in bug spray, mosquito repellent. Okay? So one equivalent of our amine is being used as the nucleophile. What do you think the other equivalent is used for? Yes, Brady. It is the base. Yes, you generate HCl. In this case, our nucleophile is a weak base, but it's basic enough to neutralize the HCl. So instead of adding pyridine, you just use 2 equivalents of your amine, and you generate an ammonium chloride salt as your byproduct. So it's the same mechanism that we have up here on the board with the alcohol nucleophile, just that we're using the amine as the nucleophile. And then in the second step, we're using our second equivalent of the amine as the base, as opposed to pyridine. So you should be able to draw that mechanism on your own. Any questions? Okay, so anhydrides look like this. The R groups can be the same or different. We'll keep them the same right now to keep things simple. And we react those with various nucleophiles. I'm going to put the pyridine in parentheses because in some cases we'll use pyridine. In other cases we won't. And we're going to get our new product here. And then we're going to get a byproduct. That byproduct is going to be a carboxylate. And it's going to be paired up with usually a nitrogen. I'm just going to draw it like this, an ammonium ion of some sort, which would either be from pyridine or from an amine used as a nucleophile. Okay, so if we're reacting an anhydride with an alcohol, we've already got that up here on the board. Let's just, whoops, I didn't want to bring that one down. Let's just bring that down just a touch. We've already got that up here on the board. So if we just replace the chloride with this carboxylate group, we have the same mechanism. Our alcohol attacks, our pyridine deprotonates. The carboxylate is here instead of the chloride. It's going to be a better leaving group than the alkoxide. And so that's what gets eliminated, and you get the alcohol, and you have chloride departing. Or you have the carboxylate departing, okay? So we use pyridine if we are reacting alcohols with anhydrides, okay? If we're reacting amines with anhydrides, that's our other one. We're typically not reacting carboxylates with anhydrides to make other anhydrides. Usually it's either alcohols or amines. If we're reacting amines with anhydrides, like we did with the acid chloride, we're just going to be using 2 equivalents of that amine. One is the nucleophile and one is the base. And so we'll just take a look at that mechanism here on the screen. Using ammonia as the nucleophile, it attacks. Then the second equivalent of ammonia functions as the base. Step 3, we eliminate the carboxylate. We have our amide product, and then we have our carboxylate that's forming a salt with our ammonium ion. Any questions about this mechanism? Yes, Lily? That's a great question. So most of the time in class, we'll use ones that are symmetrical. There are special ones where you have either a bulky R group to cause it to react with the other one, or you have one that becomes a better leaving group, so you attack at the other one. There are ways to make the unsymmetrical ones react in the way that you want, but for class, we'll just stick to the symmetrical ones. So yes, question. Why is it less stable than what? So why does this happen? Yeah, this would be kind of a 50-50 in terms of the equilibrium, but actually what happens is you have an electron donating, right? Your carbon can donate electrons in that tetrahedral intermediate. And so that's, yeah, actually, that's a good question. My explanation I was launching into was more confusing than helpful. So we'll stop with that and just say that if that were a problem, if you were having trouble driving this, you would just use more than 2 equivalents. And then Le Chatelier's principle would consume the amine. Okay? So I'm not sure if it becomes a problem or not in certain cases, but you could certainly solve that by using more than 2 equivalents. Last thing I'll show you is a reaction with anhydride you don't want to try at home. Morphine is isolated from opium poppies. It has an alcohol, 2 alcohols actually, that are reacted with 2 equivalents of acetic anhydride to generate heroin. This is an easy reaction. It's performed in many illicit laboratories around the world. Acetic acid is produced as a byproduct. Now you can neutralize that acetic acid with the pyridine, but it's very difficult to do that 100%. You're going to have a little bit of acetic acid present, okay? We learned in chapter 19 that carboxylic acids are really stinky, have very strong odors. Drug-sniffing dogs are trained to detect acetic acid, among other things. But if you have heroin in your luggage, there's a good chance that a drug-sniffing dog will sniff out the trace amounts of acetic acid that will be in there. So you really don't want to be transporting vinegar or other acetic acid products in your luggage because you might attract drug-sniffing dogs. We'll stop there and talk about carboxylic acids tomorrow.